In this example, I'm going to look at three reactions taking place in an isothermal batch reactor. They're all first-order reactions, and the rate constants are given. And the first question is, what's the reaction time to obtain 90% conversion? And then the second question is, what's the ratio of the concentration of B, the product from the first reaction, divided by the concentration of E, the product from the third reaction, when we have 90% conversion? We're given the initial concentrations in the reactor. The first thing in solving reactor design problems, make a diagram and typically write down mass balances. I'm going to write down the mass balance for component A, which is involved in all three reactions. So the change in the total number of moles of A respect to time is each of these reactions. R sub 1 represents the rate of reaction. In this case, it would represent the rate that B forms. So the rate of reaction of A has a minus sign in front of it. And then we multiply by volume to get the reaction for the total react. This is a liquid phase reaction, as are most batch reactors. And so I can separate out the volume. Right side stays the same, but now I can eliminate the volumes. I can then substitute in. So I've substituted the numerical values for K1, K2, and K3. And then important, I accounted for the stoichiometry. The third reaction, R sub 3, would represent the rate of formation of 1 mole of E, but that requires 2 moles of A, and A is reactant, that therefore the minus sign, and so the stoichiometric coefficient, then the 2 must appear in our rate expression. I've also separated variables and brought the concentration to this side, indicated that the units on the right side for the rate constant are hours to minus 1, which means our answer for time is going to be in hours. The concentrations on the left side will cancel. So I can integrate this from our starting time. We want a time to 90% conversion. So Ca 0, and because it's liquid phase, 90% conversion means 10% of the Ca is left. So this I can integrate at the log of the concentration of A, evaluate it between these two limits. And the right side, I've added up the terms in the parentheses and integrating dt is t. The limits between t and 0 just ends up with t. When I substitute the limits in here, the Ca0 is going to cancel. And I can solve now for the time for 90% conversion. So that's the first part. We know the time to convert 90%, but now we're interested in what's that product distribution, what's the ratio of those two products. The general way, we could probably do it analytically here, but it's actually just more efficient and more general to just write down the differential equations and solve them numerically. This allows us, when we have second-order reactions, more complicated systems, non-isothermal systems, to follow the same procedure. I've written here the mass balance for B, the mass balance for E, and then I've repeated the mass balance for A. Keep in mind now, in each of these, I can write it in terms of concentration. Because it's a liquid phase system, I need initial conditions to solve this, namely at t equals 0, the concentration of A is 10, concentration of B is 0, and the concentration of E is 0.50. So what I'm going to do now is just integrate these equations simultaneously. I've used polymath because it's relatively easy to set up. I'm going to integrate until the time is 1.84 hours, because that's what we determined in the first part of the problem. And so the polymath program is pretty simple. Here's the mass balance for A, the mass balance for B, the mass balance for E with the numerical values of the rate constants substituted in. The initial concentration of A, B, and E, our starting time, our final time. Polymath, then these are the differential equations it's solving. And the results are, here's the concentration of B, here's the concentration of E. Problem wants us to calculate the ratio of the concentration of B over the concentration of E, so that's 2.88 over 3.02. They have the same units, so we don't need to write them down. 0.95. Again, this is the simple way to solve the problem that allows us then to change to a second order reaction, a more complicated rate expression, and use the exact same procedure to solve.